Okay, so this is the last lecture, lecture 26. Today is the 13th of March. This is a substitution for the class we were supposed to have yesterday. So what I'm going to do first, I will start with friction because that's the topic uh, we covered last. And although we have a few problems, could do a few more. But there are a couple of things about friction that I really want to make sure you have grasped that. I said that there are mainly two types of friction problems. The type or category number one is that you're okay, explicitly, you are uh, told equilibrium exists. Okay. What it means by equilibrium is that the object is not moving or is at just the point of motion pending, or uh, sometimes is moving with a constant velocity. Still considered equilibrium. It's dynamic friction, but you can still, first law of Newton, you remember, summation of forces is equal to ma. So if either uh, the right-hand side is zero, or you have a constant velocity, which means acceleration is zero. So ma would be zero. So summation of forces would be zero. So, so that's the first type. The second type are, in this case, when equilibrium exists, force of friction, it is at its maximum value of static friction, which is mu s times n. But there are cases that you do not know if friction exists. You need to verify that. So, for instance, you're asking, okay, find what is the maximum value of the force, or let's say, if such and such force is given, is this going to stay in equilibrium? So you do solve the problem based on the assumption of the equilibrium. However, the friction force, wherever it exists, it is an unknown that is not mu s. You need to find that as an independent unknown. You find that, and then once you find that, compare that with mu s n. If it is less than or equal to that, then equilibrium exists. If not, it doesn't. So let me do a few more problems here. I'm going to do specifically two problems that are, typical and also good comprehensive problems. Okay, these are besides what you have been given. I've sent you with a solution. So let's say this is a ladder. So this guy is going, which has 75 kilogram mass. It's climbing up, and and he wants to stand at a point which is 0.25 meters from this end. Okay. We want to know if this ladder kind of opens and closes, and these surfaces, of course, have friction. What would be the best angle or the minimum angle that this guy should uh, keep this two legs together so that the equilibrium exists. So, the ladder doesn't open up, or so the guy falls down. So we want to find theta, basically. So the question is that the problem says you want to find the theta so that ladder does not slip. So what does that mean? That means friction forces exist here, but you don't want the ladder move. That means here you have the maximum friction force, and that maximum friction force is keeping this in equilibrium. So if you draw the free body diagram, this is basically a frame problem. This is part that, say, the guy is standing here. So I just show the weight of the guy, okay? And the ladder doesn't seem to have any weight. So it's just, the ladder is assumed to be weightless. So this is the weight of the guy, which is 75 times G, which is 9.81. Um, and if this ladder is going to slip, is going to slip this way. That means motion would be this way. Therefore, the friction force at A would be this way, and this is the normal force, right? Okay, so, and then at point C, what do you have? You have this piece of the ladder, but this piece of the ladder is pinned here and pinned here. So it is a two force member. So if there is a force at C, it comes from this member, which is member BC. Okay, these are not two independent uh, forces. Okay, and this is the angle. So when it comes to this free body diagram, then you have this force BC, and then at this end, again, you will have what? This leg may also slip that way, so the force of friction at B would be also this way, and this is the end at B. So these are the two free body diagrams that you need to draw. Okay, any questions? Okay. The length of each piece is given as 2.5 meter, and that's it. So what do you do? I will look at these. This is a frame problem. So I have one, two, three unknowns. Here I have also one, two, three unknowns. But I look at it and I can see that, by the way, this would be, if this is theta, this would be theta over 2, okay, because this is symmetric, okay. I look at this problem and I see that uh, although I have two unknowns here, okay, because f of b is also mu sub n, but by the way, mu's are given. This is easier to start with this one. So I start with this one. I write summation of forces along x is equal to 0. Okay, this is theta over 2. Okay, so you need to write summation of forces along x is equal to 0. So this is theta over 2, and this is theta 90 minus theta over 2. So summation of that would be a projection of this along the x-axis, that is FBC times sine of theta over 2, because the cosine of this angle is sine of that angle, minus f of b, and f of b, given that this is in equilibrium, would be 0.3 n b equal to 0. Summation of forces along y equal to 0 will give me what? Will give me f of b down, it would be nb, okay, minus f of b cosine of theta over 2 is equal to 0. So let me simplify these two equations. The first one will give you, basically f of bc, okay, sine of theta over 2 is equal to 0.3 nb. This one will give me fbc cosine of theta over 2 is equal to nb. Two equations, but three unknowns, right? nb, theta, and FBC. Okay, so what I would do, if I divide these two equations, left-hand side gives me tangent of theta over 2 equal to 0.3. So theta would be what? 33.34. So we found that theta, based on the assumption of this is going to be staying in equilibrium. Okay. However, I do not know if this f of a, which is the most important one, is adequate to keep this in equilibrium. So let's find out, assuming that if f of a that is required for equilibrium, okay, is what? Is mu times NA, which is 0.3 times NA, okay? So we need to find NA. So I'm going to use now this free body diagram, and I will take summation of moments. I go to free body diagram number 2. I take summation of moments about A is equal to 0, okay? If I do that, I have FBC sine of theta over 2, which is 33.4, okay, times, okay, this one, the two component, this component and this component, right? So this would be, okay, positive times this distance, which is, actually, I use this one. It itself is given, the distance is given 2.5, okay? And, okay, so I forgot to give that to you. This is 2. No, I had given it 2.5, yeah. So 2.5 minus the weight, which is 75 times 9.8 times, okay, 0.25, okay, equal to 0. So if I solve for this, I get f of BC comes out to be, okay, f of BC comes out to be 133.4 Newton. Okay, so that's f of BC. Now, if I write summation of forces along x equal to 0, f of A that I get for the equilibrium would be f of A minus this component of this, which is 133.4 times, and this is theta over 2. So times 33.4, sine of 33.4 divided by 2, okay, is equal to 0. So that gives me FA, that comes out to be 38.4 Newton. So this is the force that, as we assume this is in equilibrium, right? But if you make that assumption, this is a force, friction force, that is required to keep this in equilibrium, okay? Let's see if this is going to be less than this or not. So we need to find NA as well. In order to find NA, I write summation of forces along y also equal to 0. So I have NA minus 75 times 9.81, the weight, plus this component, this component of FBC. So that would be 133.4 times cosine of theta over 2, that is 33.4 over 2, is equal to 0. That will give me an A that comes out to be 607.7. So the FA that is required to keep this in equilibrium is this, okay? But let's see if friction force generates at least that much force. That's what we need, right? So the F of friction at A which is mu times NA 607.7 comes out to be 182.32 Newton. So this is the friction force that is generated. All we need is this much force to keep this in equilibrium, right? So that means this, for this theta that we found, okay, and we assume that this structure stays in equilibrium, the friction for this force is adequate to keep this in equilibrium. Okay. Any questions?
A quick one. So when you did the moment about A
Yeah.
for number 2,
Mhm.
what were we using the 2.5 for? Because it wasn't like some X or Y distance. We were using like the length of the pole
Oh,
for
sorry.
the moment.
Oh, no, no, no. I see. Let me see. This is, you have these two components. I should have done this. I should have actually uh, done this. This is, let me resolve it into its component. So this is FBC cosine of theta over 2. And this is obviously FBC sine of theta over 2. Okay, so let's see. I'm taking summation a moment about A. So this one is clear because this distance is given 0.25. Then
Mhm.
I have, I know what you mean. Oh, no, this equation, moment equation, the answer is correct, but the moment equation is not because I have taken moment about uh, point A,
Mhm.
right, would be FBC sine which times this distance, and that distance is, okay, you're correct. This is theta over 2, right? This distance would be, this is 2.5 sine of theta over 2, and this distance, right, is
Yeah.
2.5 cosine of theta over 2. So this distance and this distance I need for the moment. So the correct moment equation is FBC sine times this distance, which is 2.5 times cosine, I mean sine of 33.4 divided by 2. And I'm also missing another term. So that is positive. And then this one, which is plus FBC cosine of 33.4 over 2 times this distance, which is 2.5 sine of theta over 2. I'm glad you noticed that I had a wrong moment equation. But I had this answer, so the answer is
Oh,
correct.
gotcha.
Sure. But
Can
I'm
you
glad
move
you did.
up the paper a little bit to see the
Sure.
free body
Bring it
diagram?
up.
I mean, like the other way. Yeah. Thank
Okay.
you.
Sure. All right. So this is a good problem of second type, that you want this to stay in equilibrium, but you do not know if the force of friction that is required to keep this in equilibrium is adequate at this point. So you need to solve based on the assumption of equilibrium, find the friction force that is required to keep this in equilibrium, but then compare that with the actual friction force, maximum friction force that may develop here. So if this is less than that, obviously this stays in equilibrium. So let me do another friction
Professor,
problem. Yes?
I have a question for the moment equation about A. Why did you only use one component of FBC?
No, I use both of them. Yeah, I had made a mistake here. You see, thanks to
Oh,
Mason. He brought it to my attention that let me actually show you. It is this component. So this is FBC, okay, assigned, in other words, is the moment of this, and then moment of this component. So I have
Okay.
moment of this and this. And both are positive. Okay. And then this one, which would be negative. This goes this way, but this one and this one both generate a positive moment.
Okay, that makes sense.
Sure.
So
I'm
for
going
the
to do
di-
another. Yes?
Sorry, for the distance from the moment about A, you did
Mhm.
FBC sine 33. And then what about the 2.5? Wouldn't that be like cosine theta over 2?
Yeah, you see, let me see this. The first one is FBC sine 33 over 2, okay, times 2.5 times cosine. See, I have made more than one mistake. Cosine. So let me redo this. Clean slate, because that's not fair. I want to show the correct moment equation. So let me show it here. So this is what we have, instead of messing it up. So this is that. So here you have FBC sine of theta over 2. Here is the weight, which is 75 times 9.81, and it is at a distance of 0.25. You have these two forces, and then you have this component, which is FBC cosine of theta over 2. And this distance, this angle being theta over 2, this being 2.5, this distance, okay, so this distance is this distance is 2.5 sine of theta over 2. This is 2.5 cosine of theta over 2. So when you take summation of moments about A, summation of moments at A is equal to 0, you have negative 75 times 9.81 times this distance, which is 0.25. Then you have moment of this, which is positive. So you have plus FBC cosine of theta over 2 times this distance, which is 2.5 sine of theta over 2. And then this one, also positive. So you have FBC sine of theta over 2 times this distance, which is 2.5 cosine of theta over 2 is equal to 0. So that's better, cleaner. Okay. All right. Any questions? No? Okay. So let me do another problem here. And this is the problem I want to do. Okay. I have actually set it up because I wanted to make sure that I spend more time on reviewing. So I have set up, drawn that so I don't spend time on drawing the pictures. This is a very good problem. It is really a very comprehensive friction problem, and that's why I chose that. This is the problem statement. You do have a slender rod that has a weight, and the weight obviously acts in the middle of it. Is a weight, and it's sitting on this side, sitting on a block, and on this side is laying against this wall. This block is sitting on the ground. There are frictions along all these surfaces, and the coefficient of frictions are given. Along here, 0.4, at B is 0.6, and at C is 0.3. But this is what the problem statement is. We want to determine the largest moment applied to this rod, you see, we are applying a moment. We want to apply a moment, but we want to make sure that, or in other words, find the largest moment possible, okay, that can be applied without causing, okay, without causing, motion of the rod. Okay, this is a very good problem because it, as I said, if you think about it, it is type 2 problem. Why? Let's first pause and think about what is the problem is asking for. We don't want any motion of the rod takes place, okay? That means what? That means what happens is that at point C, if potentially it's going to move, the force of friction of maximum is generated, okay? And we do not know, okay? We do not know what basically friction force at A or B will be because we do not want any motion to take place. That is, when you apply this load, we don't want this to slip here. We don't want this to slip here. So we need to find those maximum forces. If we assume this is going to stay in equilibrium, what does it mean that no motion? That means this is going to stay in equilibrium. So what forces would be required to keep this in equilibrium? And then, based on the fact that we know what the maximum friction force would be here, see the forces that are required to keep this in equilibrium are less than those, maximum friction forces that are potentially generated. So let's do this. Again, this is a frame problem. So it consists of two parts. Part one is the rod that is laying against the wall and is sitting on this block. So if this moves due to the action of this moment, obviously this tip is going to go down. So the friction force would be upward. And if this goes down, this end would go this way. So the motion would be that way. So the friction force that is generated would be in the opposite direction. Okay. And of course, we have these vertical forces. How about the block? Block also has a weight, and the weight of the rod is given as 6 kilogram. Weight of this block is also given. The weight is, let me see, the weight of the block is given to be, 6 kilogram, and this one is, 3 kilogram. I mean, the mass is 3 kilogram, okay? So again, treat this like a frame problem. So we will start with this free body diagram and write all the equations of equilibrium. So free body diagram number one, all the equations of equilibrium. You have summation of forces along x equal to 0. That means F of B that way, okay, minus NC is equal to 0, okay? What else? You have summation of forces along Y equal to 0, okay?
Professor, could you scoot your paper so we can see the top of it?
Oh, here?
Other direction, other direction.
Okay.
Yeah, thank you.
Let me raise this so can you see the whole page because I need both of them. You need to see the whole page because we need both the free body diagram as well as the original diagram. Okay, so let me zoom this. Can you see it clearly? Right? Okay, so summation of forces along Y equal to 0. We have this force, and the weight. So you have NB plus FC minus weight, which is 6 times 7, 9.8, comes out to be 58.86 Newton is equal to 0. So that's summation of force along Y. What else you have? You can also write summation of moments about point B. That equilibrium equation is equal to 0. So if you do that, M is negative, acting in this clockwise direction. Moment of this force is -1. This one would be positive. This one would be positive, right? So you have negative M minus that 58.89 times this distance. This is given. This is 0.3. Okay. What else you have? These two forces. You have moment of NC, and that is positive, so you have plus NC. This distance is given 0.8, and then moment of FC, and this distance is given 0.6, so you have FC times 0.6 is equal to 0. So that's the third equation of equilibrium. As you can see, you have several unknowns, and with only these three equations, you cannot solve for all of them. You have 1, 2, 3, 4, right? So let's go to the second free body diagram. That is this block. If this going to move, right? If the block moves due to the action of this force, okay, is going to possibly rotate. Why? Because, you know, this force is pushing it this way, this force is pushing it that way, so it may rotate. So the block at its pending motion will be just at this point sticking to the ground. That's what's going to happen. So based on that assumption, let's use also all the equations of equilibrium here. You have summation of forces along Y equal to 0. That will give you NA minus NB minus weight of this block, 3 kilogram times 9.8. That would be 29.4 Newton equal to 0. You see, since this is a point where the block is at the point of motion, pending motion, and that's where it is really touching the ground, the reaction force would be at that point from the ground. Okay, it's almost like a roller here. Okay, except that the roller has also friction force. Now, summation of forces along X is equal to 0. You have F of A minus F of B is equal to 0, these two. And then you can also take summation of moments about this point, or can take summation of moments about the center of the block. I would take summation of moments about the center to get rid of these two forces. So I take summation of moment about O is equal to 0, and that'll give me F sub B, okay, moment of this about here, okay, and that distance is given 0.3 minus N sub B, okay, I do not know, okay, this is N sub B, right? I do not know actually where this N of A would be. I'm assuming that it is going to be at some point X, okay? So NB times X, okay, NB, that distance is X, minus the weight, okay, which is 29.4 times X is equal to 0, okay? No, actually, I have taken this as what I've considered point O. Sorry about that. That's point O. So I have three equations here, but let's see what, with the assumptions that we made. We assume that the slippage, if it occurs, would occur along C, and that causes, because we don't want any motion, if this is slips down, it causes the block kind of tip. So we know that the maximum force that exists here, F of C, would be mu sub C times N sub C, okay, which would be 0.3 times N sub C. And this X, which I said, is 0.1, because that's the point that this block will tip. So by substituting these values, I get in other words, this is these values substituting all of these equations, I get M that comes out to be 8.56 Newton meter, okay? N sub B comes out to be 50.8 Newton. N sub A comes out to be 80.3 Newton. And F of A comes out to be, of course, equal to F of B and is equal to N sub C from these equations that we wrote, comes out to be 26.75 Newton. So the forces that are required to keep this block in place, not let it move here, not let the block move here, are these. But we need to see the friction forces that are generated here, how much they are. Because if these are larger than those, that means the block is not going to stay in equilibrium. So I need to find the friction force maximum, friction force at A, which is mu at A times N at A, and that is 0.4 times that 80.3 that I found is 32.11. So the friction force, maximum friction force at A, that the friction generates is 32.11. Whereas the force that we need to keep this in equilibrium should be 26.75, so it's less than the friction force. So the friction force will keep this in place. How about at B? With any slippage takes place, the maximum friction force that would be generated there would be mu B times NB, and that is 0.6 times NB, which is 50.8, and that gives me 30.5 Newton. And still, the friction force that is generated here is greater than the force that we need to keep this in equilibrium. So what that means is no motion here and no motion here is going to take place. So for the moment that we found, okay, this structure is safe, is not going to move, it is going to be in equilibrium. So that is the moment that is going to keep this in equilibrium. So if you have a moment larger than that, there is no guarantee that this is going to stay in equilibrium. Any questions? I chose this problem because it had almost every concept in friction. Yes.
How did you find X in the moment about O equation?
Well, the X is the point that this block would tip over, right? So obviously, if this tips over, would tip over, imagine this is going to rotate, right? This is a block,
Yeah.
and it's subjected to this force, and this force is going to tip over. So it's going to tip over at point A, which I call at point O.
Mm-hmm.
Okay? And that distance was given. This distance was given is 0.1.
Okay.
Right.
Okay, thank you.
Professor, I had a question.
Sure.
I was wondering how in free body diagram 2 you went from moment about O
Mm-hmm.
to FC.
Oh, you mean how I found this one? No.
Yeah, how you went from
No,
where
no,
you
no.
were.
Free body diagram 2, let me, sort of separate them. Free body diagram gave me these equations, right? Free
Mhm.
body diagram 1 gave me these equations. But now, what I'm arguing that, I have all these 6 equations, right? How am I going to solve them? Go back to the assumptions that the problem has given you. We're saying that if this moment is applied, okay, it may slip, the bar rod may slip against this wall. We do not want that to cause any slippage here or the motion of the block, but it may slip here. May slip in the statics or the friction definition means you have a maximum friction force that develops here. So let's find that. That maximum friction force would be 0.3 times mc. Or in these equations that I had here, FC is 0.3 times mc. So if you put these here, you'll see you have 5 equations, 5 unknowns, and I solve for all of those 5 unknowns. Okay. So to begin with, you had 6 unknowns, but knowing this knowledge gave me, reduced the number of unknowns by 1. So I have 5 unknowns. So I found these 5 unknowns, most important of which is this moment that I was supposed to find. So I found the moment and all these other unknowns. I do not know if this moment is not going to rotate or move this object. So I have to verify that. How do I verify that? Well, if this is going to stay in equilibrium, the forces of friction that are generated here and here, right, should be this much. These forces guarantee that this object will stay in equilibrium, okay? But are these forces, these friction forces that are required to keep this in equilibrium, are they larger? They may be larger than the actual friction force that may be generated at this point and at this point, right? So we found those maximum friction forces that may develop here and may develop here. And these are those. Since these are larger than the force that we need to keep this in equilibrium, obviously the object is going to stay in equilibrium. Because the forces that keep this in equilibrium are less than the friction force that develops. So friction force is large enough to keep this in equilibrium. Does it explain it?
Yeah, I was still a little confused on how you were able to find the moment just by finding FC, because it still had the unknown of NC in it.
Oh, yeah, no. You should look at these equations, okay? I have 6 equations and 6 unknowns. 1, 2, 3, 4, right? 5, and 6. So I have 6 unknowns. However, one of these unknowns, which is FC, is not an independent unknown. It is related to one of these unknowns, which is MC. So I know FC. This has nothing to do with the moment. This has everything to do with the statement that the problem makes, that if this moment is going to potentially move this rod, would slip it along this wall. That is a depending motion. So the force that it may generate, the maximum force that may generate at this point is this. So we have the value of f of c related to nc. We had 6 equations, including fc. Now that we found fc is related to nc, substitute it here, you end up with 5 unknowns, 5 equations, which allows me to find all of them.
Okay.
That's what I did. Okay.
Are we told that C is impending motion, or
Correct. Yes,
Okay.
it is stated that potentially the only motion that may be allowed to happen is at point C. But we do not want any motion take place at B or A. That is the explicit sort of the guide from the problem statement.
Okay, thank you.
So we can't take the moment around the center of the block because we don't know the distances from
Correct.
like NA
That's
and
right.
NB.
You could have actually, because in logically speaking, as I said, if this block rotates, would rotate here, you could actually take some moment about here as well. But the reason I did, didn't take that because I don't know, it was easier. But you can do that.
Okay, cool.
Sure. Okay, now with this done, we have done enough friction problems. So what I was just going to do, just spend a little bit on going over what we have covered in the course. In half an hour, we'll just go over everything we've covered in the course. So that would give you a good guideline what kind of formulas and what kind of concepts you should be prepared for, or that cheat sheet you're preparing, or whatever books that you're going to mark up what you need. All right, so we started with forces, right? And the first concept we covered was the vector equation for a force. If you have a force acting along a line with two coordinates of 2 points along that line given, force is described as the magnitude of the force times the unit vector of that direction. So that's one thing you need to remember. Okay? That's number one. The second most important concept we studied was the moment, right? Moment of a force in 3 dimensions about a point B. What does the moment? Moment of a force about any arbitrary location is found by connecting that point to any point along that force. Of course, typically you're given no more than 2 points along that direction of the force. So you choose one of those, and preferably the easiest one, so that this position vector that results would be easy. In other words, if the coordinates are such that you can connect this to a point along the force, and that position vector, for instance, gives you a vector that is along the x or along the y, obviously has only one dimension, makes your life easier. But the general concept is that moment was this R cross product F. So once you have the vector equation, right, of the force, and you have the vector equation for the position vector, you set up this determinant I, J, K, okay? The second row are the components of the position vector. The last row are the components of the force, and you expand this determinant, that will give you the moment. So that was the second most important concept we introduced, which you really need to remember and be good at it. The third one, which was related to that, was a moment about an axis. Moment about an axis is nothing that is kind of an independent concept. What you're trying to do, you're given an axis D, you want to see what is the projection of the moment that this force makes when it's rotating the object about this axis. So moment about an axis, how do you find it? You identify a point along this axis. Then you take the moment of that force about that point. So the first part is exactly what you have done here. Moment about a point, right? So procedure is identical. You find the moment of this force about that point. Then you find the unit vector of this axis, okay? And then find the dot product of this moment and the unit vector of the axis. That gives you a scalar value, which is the magnitude of the moment of this force as it rotates the object about this axis. Any questions so far? So, what else we discussed? We discussed of the equilibrium, rigid body equilibrium. And we covered that in both 3D and 2D, okay? In 2D, rigid body equilibrium, okay, meant if a system is supported externally by some supports, okay, for this to stay in equilibrium, sum of all forces and sum of all moments of all forces acting on this object should be 0, right? So rigid body equilibrium consisted of 2 parts. First part is you're given an object and you only want to find the unknown forces at the support that are required to keep this in equilibrium. So we call that part 1, or external forces analysis, or finding the external reaction forces. Okay, how did you do that? In 2D it was easy. These external supports represents no more than 3 types of forces. Roller represents a single force that is perpendicular to the potential direction of motion. A pin represents 2 unknowns that are basically along X and Y direction that you set up. And if you have a fixed support, that represents 2 unknown forces and an unknown moment. So based on that, you always in 2D problems, to solve for these, you start with summation of moments equal to 0. Why? Because you typically, not typically, you have to, for a statically indeterminate problem, have no more than 3 unknowns. So you have 3 equations of equilibrium. Which one is the best to start with? Summation of moments. Why? Because you can always find a point of intersection for 2 of those unknowns. So if you consider that as the point you're taking the summation of moments about, you end up with 1 equation, 1 unknown. So quickly solve for that 1 unknown, then use summation of forces along X and Y to find the other 2 unknowns. So that's basically in a nutshell what we discussed in 2D equilibrium. 3D equilibrium is the same, except that you have 6 equations. Summation of all forces along X, Y, and Z are 0. Summation of moments about X, Y, and Z is 0. But as far as the supports goes, they're not as easy as 2Ds. So for that reason, you are most of the time, at least 90% of the time, you're giving explicit information that such and such support, for instance, represents 2 unknowns in these directions. Let's say it's a ball and socket joint. Ball and socket joint, like your hip in your own body, represents how many unknowns? All rotations are allowed. No translational motion is allowed. So socket, ball and socket joint represent 3 unknowns, X, Y, and Z unknowns. Or if you have a hinge and it says, okay, the thrust force is allowed, that represents 2 unknowns and so on. So you don't have to memorize those like 2D, but the procedure is the same, right? Similar. Summation of forces, summation of moments are 0. So that was all we discussed in equilibrium. Then we got to specific cases. How do you apply equations of equilibrium to analyze the structures? And in statics, the only structures that we covered were trusses and frames. So I gave you specific step-by-step methodical approach that I strongly recommend you follow those. Don't consider statics as a course in a calculus or algebra, that all you need to do is just set up a bunch of equations and solve them. The most important part in statics is what? What is the most important part in statics? Anybody?
Drawing free body diagrams.
Drawing free body diagrams. That is 75% of the problem. Okay? So let's start with frames. I said step number one, you first of all set up an X and Y coordinate system because you want to know what direction the forces are. If you solve for them, come out to be negative, that means the assumed direction for the force is wrong. So first step is X and Y. Step number two, draw free body diagrams of what? The whole structure, the whole frame. And in doing that, you do not take the frame apart. Even you have a bunch of pulleys and you have the tendency, oh, I should cut this cable so I see what the force is in that cable. Do not cut anything. Consider the structure as a one rigid piece that is only connected to some external supports. So you do draw the free body diagram, which consists of only the applied loads and the loads coming from those supports, right? Step after that is what? Break the structure apart, draw the free body diagram of each piece. Now, in doing so, now the most important concept is if two elements, two components are connected, and of course in frames all the connections are pin connections, right? When you make an assumption that there are two unknown forces acting at point A on member one, and member two is connected to member one at that point A, whatever directions you assume for the unknowns that act on member one at point A, right? This is AY, this is AX. When it comes to member two, at the same point, you have forces that are opposite in direction and equal in magnitude. That's the most critical one when you take these members apart. So you draw the free body diagram of all members. Then what? You start the step number three. You start with the member with minimum number of unknowns. There is a point that I mentioned as a warning. You should remember that. Note, as you're doing this, taking these members apart, what is it that you need to be very careful about and detect? What is that?
Two force members.
Two force members, yes. If you do not detect there is a two force member involved, you cannot solve the problem. You end up with more unknowns than the number of equations. So as you take these members apart, drawing the free body diagram of each member, make sure detect two force members because they only represent one unknown force at the point of connection. All right? So you start with the member with the least number of unknowns. Try to solve for as many unknown as you can. Move to the next free body diagram with the least number of unknowns until you're done. And what happens at the end? What do you end up with? Anybody? You end up with something extra.
End up with what?
A free body
You
diagram.
always end up with one free body diagram. You have to. You have to always end up with one free body diagram that you have not used, because you always have one plus number of unknowns that you need. So we use that free body diagram that you haven't used to verify the answers That is, sum of forces along X, sum of forces along Y have to be 0. Okay? So that's in a nutshell overview of frame problems. Remember the process. We always say that even in design. Process is more important than the end results. If you do the process wrong, I guarantee you end up with wrong equations. Okay? So now, trusses were a special case of frames. What was special about them? That every single member in a truss is a two-force member. So what does that mean? That means if you consider a joint of a truss, forces that are coming from those members to that joint are acting along that member that you have removed. So in trusses, you have two objectives. Either you are asked to find all the member forces. In that case, you use method of joints if you're asked to find all member forces. And how do you do that? Again, step by step. Step number 1. What is step number 1?
Zero force members.
Zero force members. You do identify all zero force members in a truss, because you may have been given a truss with 15 members. Once you identify all the zero force members, you may end up only with 3 or 4 members that you need to find. So identify. And how do you identify zero force members? This is the criteria. Do not ever forget. You look at any joint that has these criteria. There are no more than 3 forces. 2 forces are collinear. The third force would be 0. So you have 3 members coming together. 2 of them are along the same line. The third member is a zero force member. You can just simply remove that, and those 2 members as if they are continuous members. There is a special case that you have 2 joints coming together in a truss and there is no external load. Then what happens there?
Both members, force members.
Both of them are zero force members. So if you have a joint in a truss that 2 members are coming to that and there is no external load, you can remove those members. Both of them are 0. Okay? Now, in the method of joints, the only difference with method of section is that once you get rid of all these zero force members, since you're asked to find all the member forces, you start with a joint. Remember, in frames, you start with a member with the least number of unknowns. In trusses, you start with a joint with the least number of unknowns. Okay? Solve for those unknowns, then move to the next joint with the minimum number of unknowns. However, the big difference with the frame problem is when you find the answer, numerical value, that's only half the answer. You need to also make sure if that corresponding member is in tension or in compression. And how do you identify that? If you find a force at a joint, which is obviously coming from a member, is coming towards the joint, the corresponding member is in compression. If that force is moving away from the joint, the corresponding member is in tension. Okay, that's it. Method of section is the same, except what you do, you're asked to find only one unknown, one member. So what do? You always know you have no more than 3 equations of equilibrium. So you would cut that member and no more than 2 other members. Otherwise, you end up with 4 unknowns. Cut that unknown member and no more than 2 other members. Truss is cut into 2 pieces. consider the equilibrium of either of those two pieces and find that unknown member that you've been asked to find, that you've cut. And since you have three unknowns, you have to, again, remember all these basic important concepts we learned, because those were meant to save you time. Summation of moments meant to save you time. If you have three unknowns in a truss, in a truss that you've cut, that section, and you only want to find one of those members, I guarantee you the other two members intersect at a point. Consider the moment, sum of moment about that point, and you end up with finding only that force, and that's it. Do not find more unknowns that you've been asked to find. In a problem, if you've been asked to find force in member AB, only find member AB. You can find all the others, definitely, but you're gonna spend more time than needed. That's it. Friction we reviewed, so I think you should be in good shape. Any questions?
For the actual written exam part on Monday, what time is that?
Oh, the written exam part starts at 7 and ends at 8:30.
PM or AM?
Oh, PM.
Okay.
Right. Make sure you have had your dinner. Don't come hungry. So 7 o'clock.
Is there any way there's an accommodation that could be made for that? I have a presentation that may or may not go into 7 o'clock. So.
Okay, good point. For those who are taking the course on the East Coast, since this is too late, we have set up, in fact, an exception, so they can take it from 4 to 5:30. So that's what they can do. So that is 7 to 8:30 would be California time. Okay. For the East Coast people, we have set aside, so since California time 7 is 10 for them, we've given them 4 o'clock California time, which is their 7. So of course, we would email that to you today, because I have to set up all this special, special cases. DRCs are going to be given extra time. So you'll get an email automatically that would tell you the time, and also if you have any special arrangement DRC, what time you have. For instance, instead of 7 to 8:30, you have 7 to 10, things like that. So Mason, you're the one who said that you have another engagement.
Oh no,
No, that was Eric.
Oh,
Yeah.
that's there.
Yeah,
Okay.
for my
So,
C112
Eric
class.
Macius. Eric. Okay, there's another case. Okay, that requested they're on East Coast. Okay. All right. So you'll get that information.
Professor, can I ask you a cool question?
Sure.
So it's from 7 to 8:30, and 8:30 is the hard cap of when you have to submit. It's not like 8:40 you have to submit by.
Oh no, you will have 10 minutes to scan it and submit it.
Okay, so it's a hard submit deadline of 8:40.
Exactly, hard submit.
Okay.
If you miss it, unfortunately, you've missed it. So make sure that plan your time accordingly. And frankly, you have only 3 problems, and half an hour for each is more than plenty.
Professor, could you upload like a picture of your notes from today? It's kind of blurry on Zoom.
Okay, you mean which one?
Like today's notes?